Okay, in this section, we're going to talk about exponential functions. I want to review exponent rules from high school algebra classes real quick before we jump into functions of exponentials. Okay, so if you have if you have common bases being multiplied together, the rule is that you add the exponents. So in this case, this example, you'd have 3 to the 4th times 3 to the 6th, so that would just be 3 to the 10th. Okay, if you're dividing common bases, the rule is you subtract the exponents. So on that example, 7 minus 2 is 5, so 4 to the 5th is the simplified version of that. So the next rule is if you have a base raised to a power, which is raised to a power, you multiply those powers together. So for example, 5 to the 3 to the 6 is just 5 to the 3 times 6, which is 18. The next rule says if you have a base raised to the 0 power, it'll always equal 1. So that is always true. You can always plug that in a calculator if you forget it. If you have a base raised to a fractional exponent, the numerator is the power, where the denominator of that exponent is going to be the root. So for instance, we got 5 to the 2/3. This is the same as the cube root of 5 squared. Or you might remember from algebra classes that the way in which you apply the root or power does not matter. So you could take the cube root of 5 first and then square that. It would be the same result. Okay, and then the last exponent property, if you have a base raised to a negative exponent, you can make the exponent positive by taking the reciprocal of the base. So for instance, if you have 8 to the negative 2, that would be the same as 1 over 8 to the positive 2, right? Which is the same as 1 over 64 if you wanted to simplify it. On this side, we're going to talk about exponential functions. So some things to know about exponential functions is that the base will always be positive. The base will never be 1. Okay, and then these are some examples of exponential functions. So you got some base raised to a variable exponent. Okay, where in the previous chapter, we were kind of doing the opposite. We had a variable base raised to a constant power. Okay, so those are examples of polynomial functions. Okay, so we're focused on exponential functions. So let's look at something basic like f of x equals 3 to the x. So we're going to graph it, look at its graph. So we'll start with a table. We'll plug in some arbitrary values for x, like 1, 2, 3. So if you plug in 0 first, though, 3 to the 0 is 1, 3 to the 1 is 3, 3 to the second is 9, and 3 to the 3 is 27. Okay, so let's plot those points. And so you'll notice that as x increases at the same rate, the y values accelerate increasing. So on the right side of the graph, it's just taken off towards infinity really quickly. So that's a normal characteristic of an exponential function. Okay, let's plug in negative x values to see what's happening. So if we plug in negative 1, that'd be 3 to the negative 1, which is the same as 1 over 3. Okay, so I'm going to plot those. So about 0.3-ish is where that'd be. If you plug in negative 2, that'd be 1 over 3 squared as a positive power, which is the same as 1 over 9. So that's even closer to 0 than 1/3. And then lastly, if we plug in negative 3, that'd be 1 over 3 to the 3rd as a positive power, which is the same as 1 over 27. Which is getting even closer to 0, right? So you can see that as we plug in negative x values into an exponential function, we'll never get to 0. We'll just get really close. So we'll keep getting closer and closer as we go towards negative infinity. So that means that there is some kind of asymptote happening here at 0. So y equals 0 is our horizontal asymptote. The domain is all real numbers. There's no issue of plugging in any x value. The range is 0, not including 0. We'll never touch 0 to infinity. Okay, so this is the graph of f. Okay, what if we wanted to do 3 to the x plus 9? So it's a vertical shift up 9 from our previous graph. So we're just going to take our last graph and move all these points up 9 if we can. Okay. And so this also means there would be our horizontal asymptote would move up from where it was at 0 to 9. So the graph looks something like this. Again, it will not pass that horizontal asymptote to the left. Okay, so this is G. Okay, so its horizontal asymptote is at 9. Okay, and if we look at part E, if you have something attached to the exponent, like x plus 4, that'll affect it horizontally, the graph of the parent function. So if it's x plus 4, it'll move the parent function to the left 4. All right, so that will not change the horizontal asymptote since it's not going up or down, so it'll still be 0 where it was. So we're going to take all the green points and move them to the left 4 if we can. Okay, and that'll be the new graph. So again, it will not pass 0 on the left. So this is H. On number 2, we're dealing with a base of 1/3 to the power of x. So if we plug in 1, 2, 3 to look at its graph, these are the corresponding y values from 0 to 3. Okay. So very similar to our last graph, 3 to the x, but just in reverse order. Okay. So we'll try to plot these best we can, just really close to 0. And okay, we'll plug in -1, -2, -3. So if you got 1/3 to the -1, that actually flips it to be 3 over 1 by the negative exponent property, which is just 3. You know, same thing with 1 over 3 to the -2. This would flip it to be 3 over 1 to the power of 2, which is 9. And then same thing on 1/3 to the -3 would make it 27, because it'd be 3 cubed. Okay, and so it's the same graph as 3 to the x, just reflected over the y-axis. Right? You might have heard of exponential decay in a previous class, so this is an example of like decay, where these graphs are exponential growth, which we'll get into that in the future section. So the horizontal asymptote is y equals 0. Okay, the domain is all real numbers. The range is 0 to infinity, not including 0. Okay, if we were to have a negative x on the input, so like negative on the input, this would reflect the graph that we just made, f. It would reflect it over the y-axis. Okay, so we just take all those points, move them across the y-axis equidistant, and it would still have a horizontal asymptote at 0. Right? So it would look like this. All right, the most common base we see in mathematics and science is a base E. So E is an irrational number, just like pi, so it equals approximately 2.718. It's in the calculator above the ln button in blue, e to the x. So something like that. So if we plug in e to the 2, we get about 7.3891. You can plug in -3 as well. Okay, and if we plug in e to the pi, use the pi button on the calculator as well. Okay, and then e to the 0, just like any base to the 0 power, will be 1. Okay, so let's look at some compound interest formulas. So in this class, we typically don't deal with simple interest, so we'll skip over the first equation, and we'll just focus on this compound interest formula, right? So this calculates the final amount in an account, typically like a savings account, or it could calculate the final amount of a loan after a certain number of years have passed. So the variables to be aware of: A is the final amount in the account, T is the number of years that have passed, and then N is the number of compounding periods in the year. And R will be the rate as a decimal. So let's do an example. So number 4, our principal, sorry, I forgot to mention, P is our principal. That's your initial amount you invest in the account, or how much money you would take out of a loan at the beginning. So let's say $15,000 is invested. So that's our principal. Our rate for the year will be 0.025. So we got to change percents to a decimal. So you just move the decimal place to the left 2 times and fill in the zeros. You might remember that from a previous math class. And t equals 7. Okay, so we want to calculate the different amounts in our account after different compounding periods. So if we compound annually, that implies we only compound the interest once throughout the year. So we're using that formula I have highlighted. So we just plug in what we know. So 15,000, and then 1 plus 0.025 over 1 to the 1 times 7. And you can just plug this all in the calculator all at once. So all right, so typically with money problems, we round to the nearest penny. Okay, compounded quarterly means n equals 4. So we're just changing n to be 4 in the formula. Everything else will stay the same. The rate and the time. And so in the TID4 calculator, you can just go highlight what you entered earlier and just make edits to it. Okay, and then if you're to do C, compounded monthly would be 12 times in the compounding period. If it said daily, you would have 365 compounding periods in the year, and so forth. I will skip to D, since C is the same thing as the previous two. You would just put 12 in place of N. Okay, what if the interest is being compounded continuously? That's essentially compounding the interest an infinite number of times in a year. So it's easier to use this formula right here. I call it the PERT formula. So it's the principal times E to the rate times the time in years. So we only use this formula when the interest is compounded continuously. So we're going to use the PERT formula here. So 15,000 was our principal. The rate was 0.025, and then the years was 7. So show us how to put that in the calculator. So like that. And so the final amount in the count is 17,868.69. So here we're going to look at application problems of exponentials. So here we got a function representing the population of Mexico, and so it projects the growth over a certain amount of time in years since 2010. So P of t is the projected population after however many years have passed since 2010. So if I want to evaluate P of 4, we just plug 4 into the function, and we'll use the calculator. So let's see. Okay, so this is 115.479600. So what does this mean? So in 2014, the projected population of Mexico is 115,479,600 people. Okay, and part B would be the same thing, right? So, but for 75, so this would correspond to the year 2085. So you would say in the year 2085, the projected population of Mexico is 233,072,471 people. So very similar to part A. So we'll move along to number 6. So this function right here describes the number of people N of t who will become ill with influenza T weeks. So T is defined as weeks after its initial outbreak in a town with 30,000 inhabitants. Okay, the horizontal asymptote in the graph indicates that there's a limit to the epidemic's growth. So we can see that here. So, part A, how many people will become ill with influenza when the epidemic began? So that means time is 0. So we just plug 0 into the calculator. So anytime you see initial or beginning, that always corresponds to a time of 0. Okay, so we'll round to the nearest person since we're dealing with people that are infected. So when the epidemic began, that's how many people were ill with influenza. So part B says how many people were ill by the end of the 3rd week. So we want to find N of 3. So we just plug that back into the calculator. And it is much more than the first answer. So the virus has spread exponentially for sure after 3 weeks. So that many people have been affected. And the last question says, okay, why can't the spread of the epidemic simply grow indefinitely? So because there's a limiting factor of the population, right? If your population is 30,000, the virus can't go past 30,000. So why does the horizontal asymptote show in the graph? So the horizontal asymptote is representing the town's population. Of 30,000, which is, limiting the growth or the spread of the virus.